Between Nepal and Tibet in the Himalayas sits a mountain so tall that it stretches into what's known as the death zone. Temperatures here can hit minus 60 degrees Celsius. The air contains only a third of the oxygen we need to survive. And yet thousands of people have braved these harsh conditions to stand here at the highest point on the planet. Or is it? Everest checks in at 8,848.86 meters tall today, but we still don't really know if that's right. Because on a planet that isn't perfectly round, wrapped in a crust that keeps moving, measuring a mountain turns out to be way harder than you think. Hey smart people, Joe here. So someone alive in the 18th century, Mount Chimborazo in Ecuador was the tallest mountain on Earth. Then in 1808, that honor shifted to Dhaulagiri until 1847, when this one stole the title, which it only held for 5 years until Mount Everest was measured as the officially verified, definitely tallest mountain on Earth. So it's settled then, right? Well, it's not that simple. How you measure a mountain depends on how you define what a mountain is. And surprisingly, there's no universally accepted rule for what a mountain means. Even since the first official measurement of Everest almost 200 years ago, its height has changed many times. Some of that is because different people have done the measuring. Some of it's due to changes in technology, and a big part of it is because mountains aren't the massive, unchanging things that they appear to be. But before we tackle that climb, first we need to talk about how to make a mountain in the first place. You probably learned in school that the Earth's crust is broken up into plates, like a giant moving jigsaw puzzle. Mountains mostly happen where neighboring plates are bumping, grinding, or spreading apart. Just now realizing how that sounds. As those processes play out, it can change a mountain's height depending on when you measure it. You might be imagining our tectonic plates floating on the molten mantle the way logs float on a river. And that's kind of right. There are huge currents deep underground caused by heat from the core rising up and carrying molten rock towards the surface and then cooling and sinking back down. But that's not the only reason the plates move. In some places, denser crust sinks under lighter crust. And as that heavier crust falls, it pulls the rest of the crust behind it like a weight tugging on a pulley. And after that sinking crust melts, it can bubble up and build pressure until boom, you've got a volcanic mountain. In other places, plates meet like a slow geologic car crash, crumpling up the rock and shoving it towards the sky. This is how some of Earth's biggest mountain ranges formed. Everest and the rest of the Himalayas, for example, started growing when the Indian plate slammed into the Eurasian plate about 40 to 50 million years ago. And that tectonic smash is actually still continuing. You can even get mountains where plates pull apart. That mostly happens underwater at places like the Mid-Atlantic Ridge, which is the longest mountain range on Earth. These processes happen pretty much everywhere we find mountains, and not just on Earth. Some extraterrestrial peaks make ours look like puny little anthills. I mean, remember that Everest is just over 8 kilometers tall. Well, a crater ridge on Vesta, a large asteroid, is around 19 kilometers high. And a ridge around the equator of one of Saturn's moons might be even taller. And the Martian volcano Olympus Mons is as wide as Arizona and around 22 kilometers high. If Olympus Mons were on Earth, you'd need a spacesuit to hang out on the summit. It's so big that the entire Hawaiian island chain could fit inside of it. That's nuts. So why can't Earth mountains get that big? Well, for starters, the processes that make mountains are also strong enough to destroy them. Massive amounts of rock are broken when plates collide, and then they're eroded away by weather, rivers, rock slides, even glaciers. And since Earth's plates are essentially floating on a hot rock soup, if a mountain gets heavy enough, it starts sinking, basically melting from the bottom, which keeps them from achieving those otherworldly heights. And while the happy little mountains you might see in a Bob Ross painting may look nice and peaceful,
there lives a happy little mountain.
What goes on beneath the surface is pretty darn violent. In 2015, a magnitude 7.8 earthquake in Nepal made some peaks in the Himalayas instantly shorter by up to 60 centimeters. But Everest is actually still growing taller every year as the Indian plate keeps slowly slamming into the Eurasian plate. So will it hold the title of tallest Earth mountain forever? Maybe not. Nanga Parbat in Pakistan is growing faster than Everest is, and it might overtake its famous neighbor in the next couple 100,000 years or so. And because of all of these things, like weight and erosion, and even the weird fact that the pointier a mountain gets at the peak, the faster it gets worn down, there's probably a maximum height that an Earth mountain can get. And those super peaks in the Himalayas are pretty close to that. But when it comes to the title of tallest, Everest only wins if we choose to measure mountains in a specific way. Because finding the top is only half the equation. You also need to find the bottom. And that's not as easy as it sounds. More than half of Hawaii's Mauna Kea is submerged. So there's only about 4,200 meters showing above the water, but from base to summit, it's actually more than 10,000 meters tall. That's like 20% taller than Everest. And if we just look at base to summit measurements on land, then Denali wins. Everest only takes the title because most of the time we measure mountains from sea level. Everest just starts higher. But that's actually tricky too, because even sea level isn't level, thanks to physics acting on our planet. Since Earth's crust is denser in some places than others, stronger gravity creates hills and valleys of sea level all around the Earth. And forces from Earth's rotation cause it to bulge around the equator, so the radius in Ecuador isn't the same as the radius in Antarctica. So scientists basically smooth all of this out to create a mean sea level. Not like angry, I mean mean like average. That's the zero elevation we use to measure mountains against. Some of this may sound overcomplicated. Why don't we just measure mountains by the distance from the center of the Earth? Well, if we do that, Everest loses again. The maximum distance from Earth's center is actually Ecuador's Mount Chimborazo. The summit to Chimborazo is more than 2 kilometers farther from the center of the Earth than Everest's peak is, even though it's 2.5 kilometers shorter according to sea level. So if you climbed Chimborazo, you'd actually be closer to the stars than anywhere else on Earth. So couldn't we just settle all this elevation uncertainty once and for all using something like GPS? Well, satellites and space lasers can easily measure how far away the top of a mountain is, but they also suffer from that problem of deciding what bottom to use. Not to mention they're traveling on orbits that aren't perfectly circular or on a planet that's not perfectly spherical either. So when measuring how high something is using GPS, the 0 point there is set using an imaginary mathematical model of the Earth called the ellipsoid, which is different from mean sea level, and it doesn't account for any of those gravity lumps that we talked about. But these days, the commonly accepted view is to measure a mountain's height above mean sea level. So Everest gets the title of tallest, despite other mountains having pretty strong claims to the throne. So to sum it all up, it's pretty easy to figure out where a mountain ends, but not everyone agrees on where a mountain starts. So when it comes to figuring out what's really the tallest mountain, maybe first we should get to the bottom of that. Stay curious.